Hello again, everyone. Welcome to our discussion of section 3.3, where we will look at the graphs of quadratic functions in more detail. In this video, we will use some of the tools we've been learning about in the previous videos. But before that, I want to remind you to please read through section 3.3 from your book, skim through it, spend about 45 minutes on that, maybe half an hour to 45 minutes would be great. And then watch this video and attend the class and take detailed notes about things that are important to you or things that might be a question for you. And then review your lecture notes and go back to the book and solve all those problems that you saw when you read this section for the first time, but this time solve them without looking at the solutions. Do the same thing to the video. Come back to the video and without looking at the solutions that I'm giving, answer each question and then look at the solutions in the video. And of course, complete all the homework assignments by the due date and review all the previous material because this is a cumulative subject. So reviewing the previous material should not take more than half an hour for you each week. So 30 minutes each week. If you keep going looking at the stuff we've covered so far, things will stay fresh in your mind. Okay? Having said that, we can begin now our discussion of section 3.3. So one of the most important and meaningful parts of the graph of a quadratic function is the vertex of a quadratic function. That means looking at these two graphs, that means the top portion of it or the very bottom of it. Because if suppose you have a cost function that you're trying to minimize, right? We're always trying to minimize cost. So that point would be if the cost function is quadratic in nature, just like that, then the very point at the vertex is where the cost is minimal. Now suppose you have a profit function that is a quadratic function and it plots like this. Then at the point of the maximum is where your profit is at maximum. So minimum and maximum points of a quadratic function has various applications in financial sector, in business, and in science. Okay. Now, this form of a quadratic function, I mean, one form that you're familiar with, it's this form, right? F of x equals ax squared plus bx plus c. That's one form of a quadratic equation. But the part that you see here, right underneath it, is another form of writing the quadratic equation. The benefit of writing the quadratic function in this form is that right away you can tell what the coordinates of the vertex are. Okay, so in the example that I gave you, for example, say this was let's say this was a cost function of some kind, then h would be at the point the number of units that should be sold or manufactured in order to minimize cost, and k then would be the number of units sold or produced when the cost is minimal. So h and k would give you the coordinates of the minimum for a cost function. By the same token, if this function represented a profit function, which means that a must have been negative, because then the graph would look something like this. It would look upside down, and it would have a maximum point. If a is negative, that's what it would happen. And then at that h comma k would give you the coordinates for or the conditions for having a maximum profit. So that's why this form is useful if you're interested in the vertex of a quadratic function. And the way to get there, if you have that, in the last video for section 3.2, if you remember, if you have this form, you can obtain this form using the completing the square method. Remember that? So we can go from this form to this form using the completing of the square method. Okay, and this explains that. The axis of symmetry has this equation. Yes, it does, and we might just suffice with that in this course. So we won't do much about it. In the homework, you might see some questions on it. Here in this worksheet, we will do some examples with it, but it's really in trigonometry where you will see more of that being used and being asked about in that course in trigonometry, which is Math 127. Okay? In Math 127, you will look in much more detail into the parabola. Basically, a quadratic function graph is a parabola. Okay. So here, in the first question, it says, use each graph shown below to find the coordinates of the vertex, the equation of the axis of symmetry. Okay, so the equation of, so if you know the h and k, which are the coordinates of the vertex, the axis of symmetry is the equation of a line that goes through the h component or the x component. Okay, so answering that question from the graph, we can read that that point is at 2, 16. Right? That's that point. And then the equation of the axis of symmetry is the equation that goes right through the h, right? This is h, k, the coordinates of the vertex. K is 16, h is 2. So the axis of symmetry, which has this equation, would be x equals 2. Okay? Going right through the edge. A vertical line going right like that. Okay? Now, as a matter of fact, let me draw a dashed line as the axis of symmetry. Let's do that. So it would be like this. Going right through it. Like that. And then this one, once again, from the graph, we can read that the h, k, which is that point, is equal to, it's equal to -3, right? -3 right there, comma, -2. Okay? So the h, or the axis of symmetry, goes right through the h part, which is equal to -3. -3, and just like before, we can draw a dashed line right through that, like that. Okay, that's the axis of symmetry. Then number 2 says, in each of the following cases, find the coordinates of the vertex, the equation of the axis of symmetry, right? We know where the vertex is, then we can easily write down the equation of the axis of symmetry. Then graph the function, and they give us a hint, use completing of the square method, which we learned in the last video, 3.2, to find the equation of the form that. So eventually, I think maybe in this section, Yes, in this section later on, in about maybe half an hour, we'll learn about a second technique, which is a formula actually, to use to find the coordinates of the vertex of a quadratic function right from this equation. That would mean we could bypass this method of completing of the square method. So if we're interested in calculating the coordinates of the vertex of a quadratic function, we're going to have two tools in our disposal. One is completing of the square method, which we've learned about already. The second is coming up. We will talk about it, and I can just show it to you very quickly. It is this formula that can be used. We know what B and A are. So we calculate the ratio minus b over 2a. That's going to give us the h, or the x component of the minimum or maximum point. And then that value, we plug it back into the original equation. So the function f evaluated at this quantity. To evaluate the function value, or the k component, or the y component of the vertex. But we'll get to that. Okay, for now, we're going to use the completing of the square method in order to put this equation in this form. Okay. Remember from last time that when we apply the completing of the square method, the coefficient of the quadratic term must be positive 1. Right? In this case, it is positive 1. So we don't have to factor anything. All right, so we can write then f of x equals this number, this 2, which is the coefficient of the x term, divide that by 2. So 2 divided by 2 is 1. So we have positive 1. So then the completing of the square will give us x plus 1. That 1 comes here, squared. And let me put plus 3 over here. That's that plus 3. Why did I do that? Well, remember from last time, when we complete the square, we solve one problem, and then we create a problem, which we then, again, have to fix. So what do I mean by that? Here's what I mean. If you expand this, you can FOIL it or use the special product formula. Of course, I recommend strongly that you memorize the special product formula because it's so quick. You get x squared plus 2x plus 1. We end up with this expression. If you expand this, x plus 1 squared, you get this. Now compare this with what we had, not with the 3. The 3 is here. But compare this with what we have here. X squared, plus, 2x, 2x. And then plus 1, there is no plus 1, right? So what we need to do is get rid of this 1. We have solved the problem of completing the square when we wrote x plus 1 squared. We did it. But we created a problem because this 1 didn't used to exist. Now it does. So how do we get rid of this 1, this extra 1? We put minus 1 outside of the parentheses. So now when this expansion happens, this minus 1 and this 1 add up to 0 and drop out. And we end up with x squared plus 2x plus 3, which is what we started with. Okay? So then minus 1 plus 3 is positive 2, right? So then we get f of x equals x plus 1 squared plus 2. And there's our answer that we were able to find using completing the square method. Now, this form, we did this work, but it was worth it because now we know exactly what the coordinates of the vertex are, right? They are h comma k. So from here, the result is h comma k is equal to, we have x plus 1. So remember from when we talked about transformation of graphs, that we said this is always x minus h squared plus k. So if the inside goes from x minus h to x plus something, then h must have been -1. So there's a movement horizontally to the left because of that, because h is -1, and k is itself +2. Then it says graph this. Okay, so the vertex, graph the function. So we also need to know the solutions of this equation, right? We need to know the x-intercepts. So the x-intercepts we can calculate using because this cannot be factored, this is a prime equation, we can then we can use the quadratic formula to find the x-intercepts, where we know that's the vertex, but where does it intersect the y and the x-axis? We need to know that. So the y-intercept is the easiest to find, and I'll write it there. But now x-intercept, we need to write use the quadratic formula. So x equals, looking at that, a is equal to 1, b is equal to 2, and c is equal to 3, right? Looking at that, these are the terms for the quadratic formula. So then x equals minus b, so -2, plus or minus square root of b squared, which is 2 squared, minus 4 times a times c. All of that over 2. So this is going to be a complex root, so it's going to be quite awkward to graph it, but then we approximated. When I picked this example, I wasn't thinking about the x-intercepts, so I picked it so that we could apply the completing of the square method, but it's okay. I'll just approximate it. But so you know, the x-intercepts are going to be complex numbers. So x equals -2 plus or minus 4, square root of 4 minus 12. That would be square root of -8 divided by 2. So the x-intercepts are -2 plus or minus 2 square root of 2i over 2. And then if we factor the 2's, we get x, factor out 2, and the 2's cancel out, and from the denominator and numerator, so we get 2 times -1 plus or minus square root of 2i divided by 2, right? So these two cancel out. We get x equals -1 plus or minus square root of 2i. Those are the x-intercepts, but because they're complex, I'm just going to approximate them on the axis. Because in this case, we're not really interested in graphing complex numbers. In this course, that's not our focus. So then the y-intercept would be when x equals 0, right? So in that equation, substitute for x with 0, and so let me box this because that's our vertex. And so we have f of x. We can use either equation, either this one or the original one, to find the y-intercept. Okay, so then f of x equals, let's see, so we have f of x equals 0 squared plus 2 times 0 plus 3, or 0 comma 3. So that's the y-intercept, and then the axis of symmetry will go right through the edge. the vertex right through the edge component, okay? And we could also get this, I mean, I use the quadratic formula to find the complex solutions. You could also find it using this form too. Just solve this for when f of x equals 0. So 2 would come to this side, you get -2, and then take the square root of both sides, and you end up with the same complex number that, complex roots that I have here. Either way is fine. Okay, so now let's plot this as best as we can. So the y-intercept is there, 0, 3, right? 0, 3 would be that. Where is the vertex? The vertex is -1, 2. So -1. -1 and comma 2. So that would be right there. Okay, so that's why the x-intercepts are complex, because they don't fall along they do not intersect. This graph does not intersect the x-axis. Okay, so that's why the roots are both roots are complex. Okay, so we can approximate the shape of this quadratic equation and do it like that, and that point is -1, 2. Okay. Okay, so let's switch to the computer and let's graph this function using the computer and see how close we got this. Okay, so this was a manual interpretation or calculation of the information. So once I switch to the computer, you're going to see the screen blank out. So hang in there until, okay, there, we are there. So let's put in this function, which was f of x equals x squared plus 2x plus 3, right? Like that. So that's just about what we ended up with. Let's snap to the intercepts that we found, to the y-intercept and to the vertex. So the intercept was at 0, 3, right? So 0, 3, right there. The blue dot appears there. Let's label it so we can see it there. And let me zoom in a little bit. Right, like that. And also the vertex, we found that we had a minimum point here, and we found that point to be at -1, 2, right? -1, 2, and right there the green dot appears there, and let's snap to it with that -1, 2. Okay, so computers are nice. They facilitate things a great deal. So there we are. We have that. The other thing that this problem is asking us is to find the axis of symmetry. The axis of symmetry goes through the h component or the x component of the vertex. So x equals -1 right there. That purple line is the axis of symmetry, and it's equal to x equals -1. Okay? So let me go back to the dark camera again, and please don't mind the glitch in the screen as I do that. Okay, we're back. We're back on the dark cam. And here we can also write down the axis of symmetry, which is x equal -1, right? Axis of symmetry. And we can draw it with my makeshift ruler here. I'm using this page as a ruler. I hope you don't mind. Like that. Like that. Okay. All right. So the next graph or the next function is that. For this one, I'm going to approximate the, let's see, the x-intercepts, or maybe I should, let's see, is this one also a complex number? Probably not. Probably this one. This one is not a complex value, so it's good. So we can get a rough idea. Okay, so we have to use the completing of the square method again for this. So in this case, the coefficient of the quadratic term is definitely not positive 1, right? Remember, we can only use the completing of the square method only if the quadratic term has a positive 1 coefficient. In this case, what is it then? If it's not 1, what is it? Do you see? It's 1/3. So we need to factor out 1/3 from not only this term, but this x term. So let's do that. G of x is equal to 1/3 x squared. Now I need a number here such that when I multiply that number by 1/3, I get 2. The minus is minus. So I'm thinking, what do I multiply this by? What do I multiply 1/3 by to get a 2? Because the minus is already being taken care of. What number should I put here to multiply by 1/3 to end up with 2? 6, right? 6 times 1/3 is 2. So, and then close bracket, and of course plus 1 is here. Okay, so now the inside of this bracket, take a look at the quadratic term. It has a coefficient equal to positive 1, which means we can now apply completing the square method to this on the inside of this bracket. Okay, let's do that. So first though, we have this x term minus 6, right? So from this, the minus 6 divided by 2, what do we get? We get -3. We always divide the coefficient of the x term by 2 when we apply completing of the square method. Whatever that number, always divided by 2. Whatever we end up with, that becomes part of the completing the square. So then we have g of x is equal to 1/3, right? I have to be careful here, open bracket, and then I put x minus 3 squared, right? And then close bracket. Let's see. Right, let me close the bracket here. Okay, because I need this space. Of course, plus 1 comes out here. Plus 1. Okay? All right. So now we have solved the problem, which means we've created a completed square for these two terms. But we've created a problem as well. Where is the problem that we've created? Here it is. Let me expand this. When we expand this whole thing, we get x squared minus 6x. So far, so good, right? Compare this with these two terms. X squared minus 6x, x squared minus 6x. But now we have a third term here, which is plus 9. Right? Plus 9. But guess what? There is no plus 9 up here. So we've created an extra term that is not here. X squared minus 6 is there, but plus 9 is not there. So we need to get rid of this 9. Right? Because when we have that, let's see. I should have drawn this bracket a little bit closer to this one. So anyway, but we can still fix this. Let me fix this with my thicker marker here. So because of this 9, then what are we going to end up with? When you distribute this 1/3 into this, expanding this, we get 9, right? Then this 1/3 is going to multiply itself by this 9. What are we going to end up with? We're going to end up with 9/3, which is a positive 3. So we're going to end up with a plus 3 from here. 1/3 times all of that, we're going to end up with a plus 3 that we do not need, right? So then we need to get rid of that 3 somehow, which means we're going to subtract it on the outside. So I should have put this bracket a little closer here to leave myself room on the outside. But it's okay. I will work with this. So this is that. This is all belong to that. After distributing this, we end up with a plus 3. So we need to then subtract 3. And let me do that with my blue pen. We're going to say minus 3. And then plus, this plus 1 comes here. Now it's okay now. But this minus 3 should be on the outside, not on the inside. Okay? If I put it on the inside, I should have put minus 9. You could do it, you could deal with it that way too, if you want to. So if this was on the inside, it would have been minus 9, not minus 3. Minus 9 multiplied by 1/3, it would give us minus 3 again, which we would then add to this, let's see, to this 9, and eventually end up with 0. So let's see. But this should work out just fine, because 1/3 times 9 is positive 3. Minus 3 on the outside, they add up to 0. So this is better than putting that any other quantity on the inside. Okay, so let's clean this up and write it in a more clean and concise way. So g of x is equal to 1/3 times x minus 3 squared, minus 3 plus 1, minus 2. Like that. Okay. So now let's expand this. Let's expand this, and we should be able to get that original expression. Let's do that on a piece of scratch paper here. So I'm going to expand all of this. We should get this function back. Okay, let's expand this. So we have g of x 1/3 times x squared minus 6x plus 9, and then minus 2 is out here. So let's distribute the 1/3 into all of this. So we get 1/3 x squared. 1/3 times minus 6x is minus 2x. 1/3 times 9 is plus 3. Right? And then minus 2 is out here. So let's simplify this again. We get 1/3 x squared minus 2x. 3 minus 2 is plus 1. Right? So compare this. Oops, I went off the screen a little bit. But compare this with that. We have the same thing, right? 1/3 x squared over 3. That's the same thing. X squared over 3 is that. Minus 2x plus 1. Okay. So now we know where as soon as we have this form of the quadratic equation, we know what h and k are, right? From here, we can quickly write h comma k is equal to, h is this one, right? From transformation of graphs, remember? So h is 3, because the general form is x minus h. So if this minus was preserved, h must have been 3, and k must have been minus 2. So that's where the vertex is. And then the y-intercept, we can find that very easily too, right? Just substitute for x in here or here, makes no difference. If you substitute it, this one is actually easier to find, to use to find the y-intercept with. So if you plug in, so let's write this down, y-intercept is when x equals 0, right? So from here, function g at 0 is 0 squared over 3 minus 2 times 0 plus 1. So the y-intercept is, 0 comma 1. That's the y-intercept. The x-intercepts are not complex, so let's find those two, right? Because I'm running out of room here, I'm going to put the x-intercepts calculation for that up here. I hope you don't mind. Let me bring this. Okay, you can see it all. You can see it all on the screen now, which is good. So the x-intercepts we can calculate that using, let's use this form because it's easier. Let's not use the quadratic formula. Let's use this to find the x-intercepts. So 0 equals, I'm going to use this, 0 equals 1/3 times x minus 3 squared minus 2. Right? Let's use that. So multiply both sides by 3, what do we get? We get 0. We get x minus 3 squared, and we get minus 6, right? Multiply both sides by 3, and you get this. The fraction is gone, and minus 2 becomes minus 6. Right? So let's put the 6 on this side. So then we have, let's continue here. So we have x minus 3 squared. Move negative 6 to the other side. When it moves to the other side, it becomes positive 6. Take the square root of both sides. Is this correct? When I took the square root of both sides, is that correct? There is something missing. What is missing? What's missing is plus or minus, right? Plus or minus square root of 6 I meant. So I meant plus or minus square root of 6. Sorry about that. Okay, so now we can then continue here again. So we have x minus 3 equals plus or minus square root of 6. So the x-intercepts are x equals, move the negative 3 to the other side. It's negative on this side. When you move it across the equality symbol, it becomes positive 3 plus or minus square root of 6. So that is those two are our x-intercepts. So the square root of 6 is 2 point something, right? As a matter of fact, if you want, we can take the square root of 6 here. So square root of 6 is equal to 2.4, right? Let's round it to about 2.4. So 3 plus or minus 2.4, we have a rough idea of what this is going to be, right? it'll be about, so these two, we can get a rough idea about the x-intercepts. So one of them will be at 3 plus 2.4, it'll be 5.4 comma 0. The other one, it's going to be 3 minus 2.4, which will be roughly 0.6, roughly. So almost 0.6 comma 0. Okay, so we have those, everything we need to graph this. Okay, those are the x-intercepts right there. Approximations of this quantity, right? We have the y-intercept and we have the vertex. So let's plot the vertex first. 3 comma negative 2. 1, 2, 3, negative 2. So that'll be, so it'll be, these are a little bit offset, but it's just every little square. So minus 2 would be here, and 3 is there. So that's the vertex. And then, so that is 3 comma negative 2. Then we have the y-intercept, which is 0 comma 1, which is that, 0 comma 1, right? 0 comma 1. And the x-intercepts are at 5.4 comma 0. 5.4 will be somewhere between 5 and 6. So here, and 0.6 comma 0. 0.6 comma 0 will be somewhere between 0 and 1, right there. Okay, so that'll be 5 comma 0, and that one would be 0.6 comma 0. Okay, so we have a rough idea where this line is going, right? Where the graph is going. So we can come here and draw a line like that, and then hit the vertex, which is a minimum again, and come back up like this. Okay, like that. And the axis of symmetry, they also asked about that, right? The axis of symmetry is going to go right through the vertex, so it's going to go right through the edge. So x equals 3 is the axis of symmetry. And let's draw that. It's right there. And I'll try to draw it as clean as I can using this. And then we'll go to the computer and have a look at this, all of this using the computer too, like that. Okay. So let me go to the computer and I will graph this with all of these points showing. So again, please don't mind the glitch in the screen as I switch to the computer. Here is coming up right there. And so let's put in that equation, which was x squared divided by 3 and divided by 3, and then minus 2x plus 1, like that. And I should zoom out because right there, right? Very close to what we had in our manual graph. So let's snap to various points that we calculated. Let's snap to the vertex, which was 3 comma negative 2. Right there, right? That one. And we'll label it 3 comma negative 2. Minimum point, right? Now let's snap to the x-intercepts, which I couldn't, manually I could not be so precise as that number. So the x-intercept, one of it is 3 comma plus, or sorry, 3 plus square root of 6 comma 0, right there. That's that one, the right one, on the right hand side. So there it is. So it approximated where that point went. And then let's do the one that says about point something, right? We approximate 0.6 or something. But this looks like to be a little over 1. But, well, no. It's actually, that's a little bit. So I might have rounded my number too much, but this was 3 minus. The other x-intercept was 3 minus square root of 6, right? And then comma 0, right there. So let's label it. So I wrote down 0.6, and the computer said it's actually 0.55. So of course, this is a much more precise value here. Okay, so we can see that. And of course, let's graph the axis of symmetry. Axis of symmetry should go right through x equals 3, right? So we have x equals 3. That green line is our axis of symmetry. Okay, so let me go back to the dock camera again, and please don't mind the glitch in the screen. Okay, we're back. In this example, they want us to do the same thing, use the completing of the square method. And so this is, we have a coefficient here of the quadratic term that is not equal to positive 1, right? So what should we do? Do you remember what we should do? We should factor these two terms, not the 1, just these two terms. So let's factor. F of x is equal to, we're going to factor out negative 3 times x squared, right? Minus 3 times x squared is going to give us minus 3x squared. Then plot, what do I need to put here to multiply by negative 3 and get negative 3x? Positive x, right? Minus 3 times x is minus 3x. We got it. And then, of course, plus 1 is way out here. Okay, so now the inside of this parentheses is a quadratic expression with the coefficient of the quadratic term equal to positive 1. So now we can apply the completing the square method to this. So what is that number? What is the coefficient of the x term? It is positive 1, right? So from here, the coefficient of that x term is 1 divided by 2. We always take that coefficient and divide it by 2, that x term, right? So now we have 1 over 2. Then we can complete the square. So we write f of x equals minus 3 times x plus 1/2 squared, right? And then so we have, then let me put this bracket around this. So we have minus that times that, right? So this, we've completed this square. And then, of course, this plus 1 comes way out here. And then here, I left a little bit of blank space because we're going to need to subtract something from this, right? So let's see what is it that we need to subtract from this after completing this square. So I'm going to bring my scratch paper here. Well, for this piece, let's expand that. I want you to have this on the notes. So I'm going to expand this in this corner again, like the previous examples. Let's expand this piece to see how much extra than this we end up with. So we end up with x squared plus 2 times x is 2x times 1/2 plus x, right, plus 1 over 4. Compare this with the inside of this parentheses, because negative 3 is negative 3. It's happy out here. We don't bother with this. But compare this with that expansion of this with that. X squared, plus, x, x. And then all of a sudden, 1/4, right? So we don't need this 1/4. We didn't have it there, but we created this problem. Why? Because we completed this square. So when we get this 1/4, what happens? This negative 3 is going to distribute itself to all these terms, right? It's going to be minus 3x squared, minus 3x, and then it's going to give us something else that we don't need, in addition to 1, right? 1 is okay. We started with 1 and we carried it over to this and to this. But when this minus 3 multiplies itself by the expansion of this, we end up with minus 3 times 1/4, which is minus 3 over 4, right? We end up with minus 3 over 4 when we distribute this into this, because this is the expansion of all of that. So what we need to then, in this case, we're not going to subtract anything. We're going to add positive 3 over 4. Okay, do you see the reason why? Because this negative 3, it's going to multiply itself by the expansion of this, which means negative 3 is going to multiply itself by 1/4 as well as these guys. We're going to end up with minus 3 over 4. Extra. We didn't have minus 3 over 4, right? So what happens then, we need to add positive 3/4 here. So 3/4 here. So we say plus 3 over 4, then plus 1. So now, when we expand this, multiply it by minus 3, we end up with a term, minus 3 over 4, which then can be added to 3 over 4 and end up becoming 0. So we end up with the original expression here. Okay? Let's test it. Let's do this on a piece of scratch paper. Right? Well, let me complete this. Let me simplify this, and then we'll do that. So now let's clean this up a little bit. So we have minus 3 times x plus, oh, by the way, this is f of x. So let me use my thicker pen here. This is f of x equals, right? F of x equals minus 3 times x plus 1 over 2 squared. And then we should add 1 plus 3/4, right? Let's take the common denominator. How do we add 3/4 plus 1? We need to take the common denominator. The common denominator is 4. The denominator of 1 is 1. Right? We need to get it to be 4. This is okay, but this is 1. We need to make this 4 as well as this. So we're going to multiply it by 4, and then we're going to multiply the numerator by 4 as well. We can't do something to the denominator and not do the same thing to the numerator. Okay? So what do we end up with? We end up with 3/4 plus 1 times 4 is 4, divided by 4. Right? So the denominators are common. We keep it as the common denominator. Now we can add 3 plus 4. We can add the numerators because the denominators are common. So we end up with 7/4. Right? So 3/4 plus 1 is equal to plus 7 over 4. Okay, so this is, after we completed the square, this is the result. So let's test this. Let's expand this and see if we're going to get this expression. What we started with, minus 3x squared minus 3x plus 1. Let's expand all of this to see if we're going to get that. Okay, I'm going to expand this by saying minus 3 times all of this expanded, x squared plus x plus 1 over 4 plus 7 over 4, right? So, let me move this up a little bit. So let's distribute. What do we end up with? Minus 3x squared minus 3x minus 3 over 4, right? Distributing this into all the terms, plus 7 over 4. Okay? Then, what do we end up with? Minus 3x squared minus 3x. Minus 3/4 and 7/4 have common denominator, which means we can add or subtract the numerator. So minus 3 plus 7 is plus 4 over 4. So we end up with minus 3x squared minus 3x plus 1. So compare this with that, what we started with. Compare them. Minus 3x squared, minus 3x squared. Minus 3x, minus 3x. Plus 1, plus 1. So it's okay. Okay, like that. So you can always test back with the equation you had to see if completing the squared is doing what it's supposed to. And of course, we did all this. Now we can benefit from it by easily writing down the coordinates of the vertex. So h comma k is equal to, h is whatever it's inside, right? X minus h has become x plus 1/2. So h must have been minus 1 over 2, comma k, of course, is right there, 7 over 4. So that's the coordinates of the vertex, which they've asked us to find. Let's find the y-intercept before we find the x-intercept, because the x-intercept it takes more work. So first, let's find the y-intercept. So for the y-intercept, we can simply plug in for x with 0. We can use that or we can use that. It makes no difference. We pick whichever one is easier to work with. So that one looks easy enough if you substitute for x with 0. So y-intercept that means x equals 0. So this is the coordinates of the vertex, right? Let me make that clear. And here we're calculating the y-intercept. So then we have function at 0 equals minus 3 times 0 squared minus 3 times 0 plus 1. I just substituted for x with 0 in that equation here. Okay? So we end up with f of 0 is equal to 1. Or the y-intercept is 0, comma 1. That's the y-intercept. So the x-intercept is the x-intercept complex? If it's complex, I'm going to approximate it. Let's see. B squared is 9 minus 4ac. No, it's not complex. So it is a positive, but it's an awkward number. It's okay. If it's not complex, we can plot it. So let's use this to find the... so for y-intercept, I use this. For the x-intercept, I'm going to use this because it's easier. Okay? Let me put that work here. Here. So x-intercept. Which means y equals 0. Okay, so using this, we have 0 equals minus 3 times x plus 1/2 squared plus 7 over 4, right? So all of this set equal to 0 will help us find the x-intercepts. So x-intercepts. So now let's move this to the left. In doing so, this minus coefficient becomes positive. So 3 times x plus 1/2 squared plus, equals, not plus, equals 7/4, right? We just moved this piece to the left. Now, let's divide both sides by, let's multiply both sides by 4 because we want to get rid of this fraction. So multiplying both sides by 4, we get 12 times x plus 1/2 squared equals 7. Right? The fraction is gone in this case. Then let's find, let's see, so we have, we can divide both sides by 12 now to get rid of that. So let's divide both sides by 12. So we'll end up with, every step we take here is to make this x isolated. It's now part of a group. We need to get rid of these numbers, the 3, the 4, and the 12 now, and then get this x out of the parentheses in order to solve for it. Okay? So we end up with x plus 1/2 squared equals 7/12. Then let's take the square root of both sides. So we end up with x plus 1/2 equals plus or minus square root of 7/12. Right? After you take the square root of both sides, we have x plus 1/2 equals plus or minus square root of that. So let's bring the rest of this here. And let's put this arrow here, all the way from here. And then here. So that way you can follow the work later. And then, so x then, right, this x equals, let's move the 1/2 to the other side. It was positive on the left. When we move it, it becomes negative. So minus 1/2 plus or minus square root of 7/12. Right? So that's what the x-intercepts are. If you want to separate these, we can. So we can say x is equal to minus 1/2 plus, right now it's plus or minus, right? So we've combined both solutions in one. Square root of 7/12, and x equals negative 1/2 minus square root of 7/12. Like that. So those are the x-intercepts. So the rough idea about this, each of these, we can get a rough idea. For example, we can take the square root of 7/12 and then add and subtract it to negative 1/2. Let's do that. Just to get a ballpark idea of where that point is. So 7, or square root of seven 7 divided by 12, close parentheses. So 0.76. Let's round it to 0.76. So what we're doing here, we're saying minus 0.5 plus 0.76. So minus 0.5, which is the minus 1/2, plus 0.76. That's one of the x-intercepts, right? So this one is equal to that one is equal to 0.26 comma 0. How about this one? So this one is minus 0.5 minus 0.76. So it's a negative number, right? Minus 0.5 minus 0.76, which is what we approximated square root of 7 over 12 is. Okay, so minus 0.76 is that, the approximation of square root of 7 over 12. Okay, so minus 1.26, right? So this one will be minus 1.26 comma 0. Sorry, that's really in the corner. Okay, so we have the x-intercepts, the y-intercept, the vertex, and we have all the information we need to graph this equation. I'm trying to keep everything on the screen as much as I can. Okay, that should be everything. So let's plot these points. We have the vertex. Oh, by the way, so 7 over 4, what is that? That is 1 point something, right? So let's calculate this. 7 divided by 4, 1.75. So minus 1.5 is minus 0.5, which would be, this axis is way, the increments are too small, so minus 0.5 would be somewhere here, and then 7/4 would be 1.75. So it would be right here, somewhere here. Okay, that's the vertex. Then the y-intercept was at 0, 1. So right there. Okay, so because this is the coefficient of this function, it's off the screen. Let me move it a little bit into the screen. Now you can see it, right? The coefficient of the quadratic term was negative. So we would expect this graph to go upside down like that. So we would expect this to have a maximum point because of this negative in front of, negative 3 in front of the x squared term. Okay, so we expect it to be like this and have a maximum point. All right, so sorry, it looks like part of this has to, okay, this is as best as I can get it on the screen. Okay, so we got the vertex, which is that. We got the y-intercept, which is that. Now the x-intercepts were 0.260, that would be here, and negative 0.21.26. So it would be on this side, 0.26 would be on that side. Negative 1.26 would be on this side. So this graph is going to look like this, like that. Okay, that vertex is negative 1/2, 7/4. 7/4. That one, that point is, which is the x-intercept, it's 0.26, 0. The y-intercept, the y-intercept was 0, 1. And finally, this x-intercept is the negative 1.26, 0. Okay. So let's go to the computer and do a nice job of graphing this, much nicer job of this using the computer. Again, please don't mind the glitch in your screen as I switch to the computer. Okay, we're back here. Let me clean this up so we can graph this equation. So this time our equation was f of x equals minus 3x squared minus 3x plus 1, right? So here it is. Can we zoom in a little bit, maybe? A little bit, yeah, that's better. So this is the graph generated by this computer. So let's snap to the various points that we found. You can see 0, 1. Right there is the y-intercept, right? 0, 1. Let's snap to it right there. And let's label it. That's the y-intercept. Let's snap to the vertex, which was -1/2, 7/4. Right there. The red point that you see, and let's label that. So that's that. -0.5, 1.75, right? And then let's also snap to the x-intercepts. One of them was, I'm going to put in the exact value. The exact value was -1.25 plus square root of 7 divided by 12, and then comma 0. So right there, it snapped to it, right? And let's label it. So there, so 0.26. I used 0.26 and computer uses 0.264 to locate that. And let's snap to this x-intercept on the negative side of the x-axis. So that was -1/2 minus, right? Minus square root of 7/12, like that. And then comma, of course, 0. And you can see the green dot there. And let's label that. So -1.26. Okay. So maybe we can zoom in a little more. I don't know. Yeah, we can zoom in a little more. So you can still see all the various points. So more important thing is the vertex is a maximum point in this case, which is different than the previous two cases that we did, right? So let's also plot the axis of symmetry, which I didn't when I drew the manual version of this. The axis of symmetry should go straight through the h component of the vertex, or the x component of the vertex. Do you see what that is? So that should be x equals minus 0.5. Right there. It went through that vertical line, that axis of symmetry right there, went through the vertex. Okay. All right, let's switch back to the dock camera. All right. And I will complete this drawing by drawing a dashed line through the vertex here, which is the axis of symmetry, like that. And then x equals minus 1/2 is the axis of symmetry. Okay. All right. Next, we will look at the formula for finding the coordinates of the vertex. So far, what did we do in the previous examples? We used the completing the square method to rewrite the quadratic function in a different format, and this format in which we wrote the original quadratic equation in could tell us the coordinates of the vertex immediately, right? We could clearly see the coordinates right there. But what about if we don't want to do that? If we don't want to apply completing the square method, can we still know what are the coordinates of the vertex using this original equation for a quadratic function? And the answer is yes. The answer is yes, and the formula to use in a situation like that is this. So let's apply it in these cases, and please read this on your own. It says the coordinates of the vertex h comma k can be calculated using this formula. Okay, very, very important. So if you're asked on an exam to find the coordinates of the vertex of a quadratic function, if you don't want to use the completing the square method, if the question is not asking you to use the completing the square method, then you can use this method. You can use this formula. So it says in each of the following cases, find the coordinates of the vertex, determine whether the vertex is a point of minimum or maximum, state the value of the function at its minimum or maximum, state the range of the function, and state the interval over which the function is increasing or decreasing. Okay. So using this formula, we already know from applying the quadratic formula, we know that a here is equal to 1, b is equal to 4, and c is equal to -5. We know that, right? We don't really need c, so a and b we can use. So let's find the x component here, which is equal to minus b over 2a, right? That's the x component. Okay, so minus b, which is 4 over 2a, which is 2. 2 times 1 is 2, is equal to minus 2. Right? That's the x component. What about the y component? The y component is simply saying, this formula is saying, take the value of x, or minus b over 2a, which you found here, and replace it inside the function to find what is the value of the function at -2. And that will be the y component of the vertex. So let's do that. So y is equal to the function at -2. The function at -2 is equal to the y component. Okay, x comma y is equal to that. So that means, let me substitute for x with -2 here. -2 squared plus 4 times -2 minus 5. What do we have? -2 squared is positive 4. 4 times -2, minus 8. Minus 5. So we have minus 13 plus 4, we get minus 9. Okay, so the coordinates of the vertex are, so because of this and this, because of these two, the coordinates of the vertex are -2 comma -9. Like that. Then what else did they ask us for a bunch of things, don't they? So determine whether the vertex is a point of minimum or maximum. Well, look at the equation. The coefficient of the quadratic term is positive. So this graph opens right side up. If it opens right side up like a bowl, then it must have a minimum. So this is positive, the coefficient of the quadratic term. Means the graph looks like that, so it must have a minimum. So this vertex is a point of minimum. And state the value of the function at its minimum or maximum. The value of the function at minimum is -9. We already know that. So which is, I guess they're asking to summarize that. So we can easily write the value of the function at -2 is equal to -9. And I will box that, function value, or value of the function value at minimum. Okay, what else they're asking? State the range of the function. So because this is vertex, and because this is opening right side up, so this is the minimum point. After that, the quadratic function is going to increase without bound. That means it's going to go from -9 to range-wise. Range means give the interval of over which the function will vary from minimum to maximum. The function value, not the x, not the independent variable value, but the function value, this one. That range has to do with that. But we know it starts with this because this is a point of minimum. So the range is equal to bracket -9 comma infinity. That's the range. Okay? State the range of the function. State the interval over which the function is increasing or decreasing. Okay, so let me draw a graph here on this piece of scratch paper. Maybe, if you don't mind, let me use this as a scratch paper here. Well, no, let me pick a better sheet here if I can find. Okay, I'm going to use this. So we know that this point is a point of minimum, right? Let's roughly sketch it. So -2, -3, so that's -1, -2, and then -9. 1, 2, 3, 4, 5. Let me move this up a little bit. 6, 7, 8, 9. Right? So this is -9, -8, -7, -6. This is just a rough sketch to make a point. So like that, right? So -2, the vertex -2 comma -9, that point is located at -2 comma -9, right there. And we know this graph, this is a point of minimum. We know that. So this means the graph must come like this and go like that, right? And they're asking us to give the interval over which this function is increasing or decreasing. Well, from here to here, that means from, and that's -2 comma -9, right? From negative infinity to -2, the function is decreasing, right? The coordinates of the vertex has a lot of information attached to it. So we can, and this question is demonstrating that we can extract all kinds of information from the vertex, right? If we know where the vertex is, we can give the range, which we just gave. We can now tell from where to where the function is increasing, from where to where it's increasing or decreasing. Okay? So with respect to the x-axis, from -infinity to -2, from here to here, the function is going down, looking from left to right, it's moving downhill. So it's decreasing from -infinity to -2, and I have to put a bracket there. To -2 is decreasing. And I'm going to clean this up before I write it on the paper there. Okay, it's decreasing. But from -2, we're talking about the x-axis now, right? Not the range. The range we already talked about. But for where the function is increasing or decreasing, we always reference the x-axis, not the y-axis. Okay? So with respect to the x-axis, the function is increasing right after -2. Right? Right after -2, x equals -2, which is right there, the function switches from decreasing to increasing. So from -2 comma infinity all the way to positive infinity along the x-axis, the function is going to keep growing and growing and growing. Okay? So if you have questions, usually when I talk about this stuff in class, there's always somebody asking me, well, why did you include -2 here and not here? There is no preference here. If you choose, you can exclude it from here by putting a parenthesis and include it here by putting a bracket. That would be just as valid. Okay, so let me then write that down. So decreasing over -infinity comma -2 bracket, and increasing over the interval parenthesis -2 positive infinity. Okay, like that. Okay, so we have part B here, part B. It says do the same thing basically. Find the coordinates of the vertex and then answer all these different questions. Where the range is, where the function is increasing and decreasing, and all of that. So let's find the vertex using this formula, of course, right? Not using the completing the square. Completing the square was one method to find the coordinates of the vertex. Here, we're going to use this formula. Okay, so x equals to minus b over 2a, and in this case, we have a is equal to 1/2, b is equal to -3, right? And c is equal to 5/2. So minus b over 2a would be minus -3 over 2a. 2 times 1/2 is just 1, right? 2a. 2 times 1/2 is just 1. So we end up with positive 3 for x component. What about the y component? Well, we can calculate the y component by simply replacing x with 3 and calculating what the function value would be at 3. By the way, I forgot to mention, but I hope you're pausing the video and you're carrying out all this calculation on your own before looking at my solution. Okay? So please do that if you haven't already. Pause the video and just finish it and then come back to the video. Okay, so I'm assuming you've done that. Now we're calculating the y component here. So y is equal to the function value at 3, x equals 3. So 1/2 times 3 squared minus 3 times positive 3 plus 5/2. Okay, so what do we get? We get 3 squared is 9. 9 times 1/2 is 9 over 2. Minus 3 times 3, it's minus 9 plus 5/2. So what is the common denominator here? The common denominator, of course, is 2. These two fractions are okay. They're happy. They have a common denominator that is equal to the common denominator. So we won't bother with these. But this guy has a denominator equal to 1, right? So how can we get the common denominator for this? Well, we have to multiply the denominator by by 2, not 9, by 2. 2 times 1 is going to give us 2 for this term. But we can do something to the denominator and not do the same thing to the numerator. So 2 over 2. So we're multiplying 9 by 2 and then 1 by 2. Okay, what is that going to give us? Let's see. 9, we didn't have to multiply this 9 by anything, right? So just 9 minus 9 times 2. We had to multiply the numerator and the denominator by 2. So 9 times 2 is 18. And 5/2 was happy too. So we didn't have to multiply this fraction by anything. So plus 5. So we end up with 9 plus 5 is 14. Minus 18 divided by 2. 14 minus 18 divided by 2 is minus 4. Divided by 2 is minus 2. So the coordinates of the vertex are 3 comma negative 2. Okay, so we have the vertex is at 3 comma negative 2. Then they ask us, is this a point of minimum or maximum? Well, we can answer that question by looking at the coefficient of the quadratic term. Is it positive or negative? It's positive. If it's positive, that means this curve is opening right side up, like a bowl, just like that. So if it's opening like that, does it have a minimum point or maximum point? It has to have a minimum point, right? Just like the previous one. It's going to open like this because the coefficient of the quadratic term was positive. So it's going to open like this, and which means it's going to have a minimum. Okay, so this point is a minimum. Then what else they ask us? They say that, I'm reading from the problem statement, state the value of the function at its minimum. The value of the function at minimum is negative 2. That's what we calculate. We're calculating, when we're calculating the y component of the vertex, that's what we're calculating, the value of the function at minimum. So the function at 3 is equal to negative 2. So this is function value at minimum. Okay. All right. So what else they ask us? They ask us to give the range. Okay. So if this is the minimum, then after that the graph is continuously increasing. That's the minimum with respect to the y-axis. So if we plot this really quickly, just trying to visualize what's going on here, we know that 3 comma negative 2 would be that point, right? This is 3, that's negative 2. 3 comma negative 2 is that point, and we know that the graph is going to do this. It's going to open right side up, and it's going to have a minimum. We know that. So what is the range then? The range, if you remember from earlier videos or earlier lessons, is the range is the behavior of the graph with respect to the y-axis. So with respect to the y-axis, the graph is beginning from negative 2, right? Negative 2, that's the lowest point. So bracket negative 2, comma, and it rises up towards infinity. With respect to the y-axis, that's the behavior we see. So the range is that. Range is equal to negative bracket negative 2 comma infinity, like that. Okay. So then they ask us that where is it decreasing or increasing? Let's go back to the same graph, right? Where is it decreasing? Well, it's coming down from this rough sketch. We can get so much information because we know where the vertex is. So this graph, we read graphs from left to right. So it's decreasing from negative infinity, that means from along the x-axis. It's decreasing from negative infinity because if you continue this line, look at the behavior of it with respect to the x-axis. It keeps going this way, right? So it's coming from negative infinity all the way to 3. From negative infinity to 3 along the x-axis, it is decreasing. And then from 3 on the x-axis, all the way to positive infinity, this way, it is increasing. So let's write that down. I hope that explanation helped. So from negative infinity all the way to x equals 3, it is declining. Then after 3, all the way to positive infinity, going this way along the x-axis, it is increasing. Okay, let's write that down. So it is decreasing on negative infinity all the way to 3, bracket, and increasing from 3 comma positive infinity, like that. Okay, so that's all the solution for that problem. So this one, if you haven't done this already, please go ahead, pause the video, and complete the solution for this, and then come back. Okay, I'm assuming you've done that. So we look at this function, and once again, we have to find the coordinates of the vertex, right? So A is equal to -2, B is equal to -24, and C we don't need, right? C, never mind. So x component, applying that formula at the top of the page, is minus b over 2a. So then minus b is minus 24. 2a would be 2 times minus 2. So we have minus 24 divided by minus 4. We have 3 negative values multiplying each other, so we're going to end up with minus 6. Okay, that's the x component of the vertex. What about the y component? Well, we replace the x with this minus 6 inside here, and we calculate the value of the function. So the value of the function at negative 6 is equal to minus 2 times minus 6 squared minus 24 times minus 6 minus 64. Okay. Okay, so now let me grab my calculator here. So let me put that here. So we have the function value at negative 6 is negative 6 squared is positive 36, right? Times negative 2, it's negative 72. Minus 24 times minus 6. 144, positive 144, right? Minus times minus is positive. Positive 144 minus 64. So the function value at negative 6 is equal to all those numbers added and subtracted. So minus 72 plus 144 minus 64, 8. Okay, so we found the coordinates of the vertex. The vertex is at negative 6 comma positive 8. Okay. Then let's answer the other questions. The first of which is this vertex a point of minimum or maximum? Well, take a look at the coefficient of the quadratic term here, the minus 2. It's a negative, right? Because it's a negative number, then the graph must be opening upside down. So if we go to this vertex, let's plot this point, negative 6 comma 8. So that's negative 6 comma 8. 1, 2, 3, 4, 5, 6, 7, 8. So that is the vertex, negative 6, comma 8. I'm using my scratch paper. That's why you see all those lines up and down the page. So that's the vertex. And because the coefficient of this quadratic function is negative, right? Look at that, negative. So this line, this graph, it's going to open like this. So that's going to be a maximum point. So this is going to be a point of maximum. Okay? All right. Next, they ask us to give the value of the function at the minimum. So the value of the function at minimum is 8. So let's see. So the function value at negative 6 is equal to 8. Sorry, maximum. I meant maximum, not minimum. So the value of the function at maximum, function value at maximum is 8. Okay? Then they ask us, what is the range? Well, the range is, let me bring back this crude drawing that I did. Because we know where the vertex is, which is at negative 6, comma a, so then from left to right, when you read the graph from left to right, is the function increasing or decreasing? It's increasing, right? Going this way. I know I drew these arrows at the ends because I meant to indicate that the lines are continuously moving, or continuing on both sides. That's all. But when we read the graph from left to right, it's increasing from this way. So it's increasing, the graph is increasing from negative infinity all the way to negative 6. It's increasing. Oh, did we give the range? No, we didn't give the range. So we also have to give that. Well, let's do that first, since that's the order in which we calculated the information. So the range for this is, because that's the maximum with respect to the y-axis, right? Whenever you give the range, the values are with respect to the y-axis. So with respect to the y-axis, we're coming up from negative infinity all the way to a maximum of 8. So here is the range. The range of this function is equal to comma negative infinity. The smaller number is always written first, and then the larger number. So it's coming up from negative infinity, reaching a maximum of 8 bracket. Okay, that's the range. Now let's discuss where the function is increasing or decreasing. So let me bring this down a little bit, like that. Okay, so it is increasing, reading the graph from left to right, it is increasing from negative infinity all the way to what x value? Negative 6. It's increasing from negative infinity to negative 6. So we have increasing over negative infinity, comma, negative 6 bracket. Okay, then it comes back down again, so it's decreasing after that. So decreasing from negative 6. I use bracket here, so I'm going to use parentheses here. From negative 6 to positive infinity all the way here, right? This line is going to continue towards positive infinity. It is decreasing from here like that, going like that. So increasing over this interval, negative infinity to negative 6, and then from negative 6 all the way to positive infinity, it's declining. Okay, so let's write that down on the paper. So the function is decreasing. I just wrote decreasing because that's what I did first there. So it's decreasing over the interval parenthesis negative 6 comma infinity, and increasing for the interval that is equal to minus infinity comma negative 6 bracket. Okay, and that's that. I hope this is clear. And so what we learned on this whole sheet, on this one page, was very important. We learned a new way, or a different way. If you had seen this method before, then it would be a different way to calculate the coordinates of the vertex of the quadratic function. And earlier I mentioned why we care so much about the coordinates of that vertex, because in the real world, that point represents things that are important to scientists and economists and business people. Okay, because of that, where the function is minimum or maximum, that has significance value in the real world. So we knew how to use the completing the square method to find the coordinates of the vertex, but this formula, this one, gives us another way of calculating the coordinates of the vertex. Okay. Next, we have a few word problems that will be based on the skills we learned or we worked on in this section. So let's read this one. It says a model rocket is launched with an interval velocity of 150 feet per second from a height of 40 feet. Okay? The function that, given to us, gives the height of the rocket. That's the height, so let's label this. So this is a physics. This comes to us from physics. So that ST represents the height of the rocket, right? Gives the height of the rocket in the sky in feet, T. So T is, let's see, gives the height of the rocket in the sky in feet, T seconds. So T is time in seconds. Okay? In seconds. That's an S, not a 5. So that's time in units of seconds. So after it has been launched, determine the time at which the rocket reaches its maximum height and find the maximum height. Well, this is just a real-world application of what we already have been doing, right, on the previous sheet. So we have a quadratic equation, right, don't we? It has a negative coefficient, which means it's going to be, when you graph this, it's going to be upside down. So it makes sense to look for a maximum point, right? Because this is going to open upside down because of this negative coefficient. So we can use the formula we just learned, that one, to calculate the coordinates of the maximum. And guess what that would be? So what, in this case, the interpretation of the x, in this case we don't have x, right? We have, what do we have instead of x? We have time, t. So when we calculate that value, minus b over 2a, it's going to tell us the time this rocket, the time in seconds after launch, which this rocket reaches its maximum point, okay? And then when we plug in that t value back inside the function, it's going to give us the height, the maximum height to which the rocket reached. reached. Okay, let's do that. So we have the x component, or t. T is equal to minus, that's time to reach the maximum, right? Time to reach the maximum, t, minus b over 2a, right? And here, a in this case is minus 16, and b is equal to 150. So minus b, 150, divided by 2a, which is 2 times minus 16. So what do we end up with? We end up with minus 150 over minus 32. Minus over minus is positive. So 150 divided by 32. Okay, so that should be, let's see what that number is. It should be something decimal with decimal value, I think. So 150 divided by 32, 4.6875. Let's round that to 4.7, right? 4.7. So almost 4.7. So when they say determine the time at which the rocket reaches its maximum height, that's what it is. So that seconds after launch, when the rocket reaches its maximum. Okay, so they also want to know the maximum height. Okay, so that all we have to do is plug in this time, this rounded time, into this equation and calculate the maximum height. So the height at 4.7 seconds is equal to minus 16 times 4.7 squared plus 150 times 4.7 plus 40. Okay, the rest becomes algebra. Let's calculate all these different numbers. So we have, let me move this up, move to the left a little bit so you can see everything. Okay, so 4.7 squared is 22.09. Now multiply that by negative 16 times 16, and then I'll add the negative to it. So we have that quantity. I'm not going to round that. I'm going to include everything here. So minus 353.44, right? Plus 150 times 4.7. 150 times 4.7. What do we got? We got 705 plus 40. So let's add all these up. So we have 705 plus 40 minus 353.44. So we got 391.56, and they tell us in feet. So 391.56 feet. That's the maximum height of this rocket. Like that. So the maximum height for the rocket. So when I took my physics course, the interesting question at that point is, okay, what is the speed of the rocket at that point? It's 0, right? It reaches at that maximum height, the rocket has 0 velocity, no speed, and then it comes back down again after that, all right? Okay. So I forgot to mention, but I hope you, by now, during the semester, you have gotten into the habit of working out these problems before me, pausing the video repeatedly, and then comparing your solutions with mine. I hope by now that has become a habit for you. These videos are not meant to be watched as if we watch movies or something like that, okay? So you must pause repeatedly and do this work on your own and then compare. They are meant for you to compare your work with this work. Okay, so this question, it says, a 4th grade class decides to enclose a rectangular garden. As soon as I read a rectangular garden, I'd like to draw a picture of a rectangular garden like that, using the sides of the school as one side. So this, let's say this is the school, right? Let's say that side, that's the school. Okay? So that's on that side there is a school wall or something. So apparently no fencing is required. That's the point of that statement. If the school wall is on one side, then there is no fencing needed for that portion, right? Because the school wall provides the fencing for that side of the garden. So this kind of garden then needs fencing on 3 sides: this side, and that side. Okay. As one side of the rectangle. What is the maximum area? So they want us to maximize the area, right? That's what they're asking. What is the maximum area that the class can enclose with 32 feet of fencing? What should be the dimension of the garden? What should the dimension of the garden be in order to yield this area? Okay, so let's give, as I mentioned before, when we solve word problems, we must introduce our own variables. That's one of the part of the strategy to solve word problems. So let's say that this is the length and this is the width, right? Length and width. Then we know that from elementary geometry. So we know from elementary geometry that the area of a rectangle is simply length times the width, right? Length times the width. We know that from elementary geometry. Then we are told that the fencing material that is available for us is, or the fencing length for the whole thing, for these 2 sides and this, should be 32 feet. Okay, so if we know the whole thing, the W and the W, so the W and W, this is a rectangle. So then we know that W plus L, that length must be equal to 32 feet. So let's write that down. So W plus L must be equal to 32 feet. Okay? Okay, so now we can use this equation that is about the perimeter of this fencing region, 2 widths and a length. We could use that to rewrite one of these variables in terms of the other one. And by the way, let me simplify this. So this is 2W plus L equals 32. Okay? Like that. So we know that from elementary geometry, and that reduces to that after simplifying. Now we can use this to write one variable in terms of the other one. That's the use of this information. So let's do that. So we can write, I'm going to write this in terms of the length, that length, okay? So, or do I want to do that? Let's see. Yeah, that would be better. So length is equal to 32. Move this to the other side, this 2w. It's positive on this side. When you move it across the equality symbol, it becomes minus 2w. Now, in the formula for the area of a rectangle, substitute for L with this quantity. So the area is now equal to, instead of L, put all of this, because that's equal to L. 32 minus 2w times, that's L, times w. Right? So now, let's distribute this w into what we have. We have area equals w times 32 is 32w. W times minus 2w, it gives us minus 2w squared. So check this out, because this is a quadratic equation, right? This is a quadratic equation that we can write in terms of w. So let's do that. So we have the area in terms of w, the function area in terms of w is equal to minus 2w squared plus 32w. So we have a quadratic equation. The coefficient of the quadratic term is negative, which means we're going to have a maximum, right? Because the curve, if you graph this quadratic equation, it's going to be an upside down curve, which means it's going to have a maximum point. So it makes sense to maximize this equation for area. We have an equation for, we've developed an equation for area by doing what? By introducing variables, right? We introduced variables, and then we remembered from elementary geometry what the area of a rectangle is equal to. So using these variables and that equation from basic geometry, we developed this equation. So now they're asking us, what should the dimension of the garden be in order to yield this area, to maximize the fencing area for this garden? Okay, so we know the formula that gives us the maximum W, right? Once we know that, we can plug it in here in this equation to calculate the length. So first, let's find the W. So that would be W is equal to minus B over 2A, right? Here, A is equal to minus 2, and B is equal to 32, right? Looking at that quadratic equation that we've developed. So then I'll come here and write W is equal to minus 32 divided by 2A. 2A, that's 2 times minus 2, which is, well, let me write it, 2 minus 2. So we get minus 32 divided by minus 4. Minus minus is positive. 32 divided by 4 is 8. So the dimension at maximum, the dimension W at maximum is 8 feet. So let's write that down. W equals 8. So width can be anything, right? But they want us to give the dimensions such that the area of that garden is maximal. And to maximize the area of that garden, given this much fencing, 32 feet of fencing, it's going to have to be such that the width is 8 feet. So this is 8 feet. And then the length, let's calculate the length from here. So length is equal to 32 minus 2 times 8. So this is 32 minus 16, or 16. So the length should be equal to 16 feet. So 8 times 16, which is 128, I think. Yeah, 128 square feet would be the maximum area given this kind of fencing. So 8 times 16. So 8 times 16 would be the maximum. 128 square feet would be the area, but these are the dimensions of the W and L. Okay. All right. So number 6, it says in business we know that, so, excuse me. So this formula is now the formula we need to use for this business context. So please pause the video, solve this problem on your own, and then come back to the video after that. Assuming you've done that, so it says total profit is equal to total revenue minus total cost, and that is symbolic version of that same statement, where X is the number of units manufactured or sold. In each of the following cases, find the maximum profit and the number of units that must be sold in order to yield the maximum profit. So here, they're not giving us the profit function right away. They tell us that the revenue function is this, and the cost function is that, so they give us these two, and then they'll say, how do we, at which point, find the maximum profit and the number of units that must be sold in order to yield the maximum profit. So we need to find the profit function. At this point, we do not yet have it. How do we find the profit function? Using this formula. We have the revenue function. We have the cost function. We subtract the cost function from the revenue function according to this formula to obtain the profit function. So let's do that. So the profit function then is revenue function, which is 5x, minus all of the cost function, all of it. Not just this one, all of it. So minus 0.001x squared plus 1.2x plus 60, like that. Okay, so let's simplify. 5x minus, we have to distribute the minus into all the three terms, not just one, all three. So minus 0.001x squared minus 1.2x minus 60. Okay, so let's put this in the descending order of power, and also let's combine 5x minus 1.2x. So the profit function is equal to minus 0.001x squared minus 1.2x plus 5x, it is positive 3.8x minus 60. So once again, we have a profit function that is quadratic in nature. And look at this coefficient. It is negative. It is negative. That means the quadratic graph opens upside down. If it's opening upside down, so it must have which one? A minimum or a maximum? A maximum. Yes, a maximum. So let's find the point of maximum. And they want us to find the maximum profit. So once we find what X value will maximize profit, we also have to find the maximum profit and the number of units that must be sold in order to yield the maximum profit. So they want us to find X and P of X, which is the same thing as we did with the purely mathematical problems where we found the vertex of the coordinates of the vertex of the quadratic function. But in this case, because it's a word problem, that coordinate, those components X and Y have a real world meaning. Okay, let's do that. So here, in this case, we have A equals minus 0.001, B is equal to 3.8, right? So then the X component, and this is the number of units that must be sold in order to yield the maximum profit, right? We're calculating that using that formula, minus B over 2A, equals minus, that minus B, which is 3.8, divided by 2 times A. 2 times minus 0.001. So we have minus 3.8 divided by minus 0.002, right? We have 2 minuses here. So minus times minus is positive. So let me calculate this quantity here. So we have 3.8 divided by 0.002, and of course that's positive. So 3.8 divided by 0.002, 1900. So that is the X number of units that must be sold to realize maximum profit. That's X. What about how much is the maximum profit? Okay, so let's calculate that. So the maximum profit is, let's plug this in. So profit at 1900 is equal to, so this is our profit function, right? That's the one we're maximizing. Is equal to, I might have to stack because I'm running out of space here. So pardon me if I wrap this around. So minus 0.001 times 1900 squared. Sorry for this, but I'm going to have to stack these terms on top of one another. Plus 3.8 times 1900, right? I'm plugging in here. Minus 60, right? So let's do the algebra. So the maximum profit then, let's calculate that. Well, maybe I did that too early. So we have, let me move this up so you can see it. And move this over a little bit. Okay. So 1900 squared is that number, times, multiply that by minus 0.001, times minus 0.001, close parentheses, minus 3000. So minus 3,610, right? That plus 3.8 times 1900. 1900 times 3.8, 7,220. Minus 60. Okay? So let's add and subtract all those numbers. We have minus 3,610 plus 7,220 minus 60. What do we get? We get a profit of 3,550. So this is the maximum profit. Okay, that's the maximum profit. How many units must be sold in order to realize this profit is 1900 units. Okay. All right, I hope that this lesson helped you grasp the concepts that this section is talking about. So thank you for persisting through this video, and for now have a nice day, and I'll see you again next time.